We do have one more presentation about data quality. So we've talked a lot so far about data, but how do we know our data are good? And so I'm really looking forward to this talk from Matt Gunshor from CIMMS. I snooped a little bit on his presentation, and I'm really excited because the file size was massive. So I'm looking forward to some pictures and maybe some animations. Let's welcome Matt.
I need to share. Slideshow mode works. Great. So yeah, thank you for that introduction, Kim. And it is a massive, massive PowerPoint. I do encourage you to download it if you're interested because there are links in there. So yeah, my presentation is on data quality, specifically the GOES ABI is what I'll be talking about because that's my area of expertise. I've been working on the ABI since 1999. It launched in 2016, so you can tell I've been at it a long time. So I have some co-authors down there to thank at CIMMS, which is a cooperative institute with NOAA. So we have NOAA people embedded in our group, and one of those is Tim Schmidt. And then Bill Line is another key member of our GOES-R imagery team. He's actually up at CIRA, which is in Fort Collins. And then some of my CIMMS colleagues on here that are mostly just on here because I stole their stuff and put it in my presentation. They may or may not know. So before I get too into it, this isn't a super hands-on interactive presentation today, but if you want to go to this link, we call this the link of links. It's just a giant shopping list of things that are useful for GOES. It's not totally unorganized, but not super well organized. But if you know what you want to look for, you want to look for something about calibration, you want to look for documentation, you want to look for, you can Control F in that page and see it. So for NOAA, GOES is all about the continuity of the mission. So, you know, from 1975 till now, they've had imagers up on geostationary platforms. Originally just one, but eventually, you know, it goes east and it goes west. And what we'll be talking about today are the imagers, the Advanced Baseline Imager, ABI, that's on GOES 16, 17, and 18. And so a key thing about data quality, of course, is getting to know your data. So some of that's going to be reading documentation. So I have a link here to the GOES-R data book. There's tons of information in there, but just key concepts if you're not familiar with ABI data, that things that might come up are the different sectors. So on here you can see, I don't know if my mouse is showing, oh, I switched slides because I tried to click my mouse. So a full disk is this whole, you know, everything GOES can see. And then it has what they call a CONUS sector, which is this dotted line. And then these two mesoscale sectors. The full disk and the CONUS are stuck, you know, those are, you get that's what it is all the time, but those mesoscale sectors can be moved around. And so you get a full disk every 10 minutes, the CONUS sector every 5 minutes, and these mesoscales every 1 minute. ABI has 16 spectral bands. So again, getting familiar with your data, you can look these things up. There's 6 visible, near visible, or near infrared bands, and then 10 infrared bands. And here's a spectral response function for the visible and near infrared bands. You can see there's one of these bands is in the blue part of the visible spectrum, one's in the red, notably no green. And then these are the infrared spectral response functions, and that's 16, 17, and 18. I'm just scrolling through them so you can see they're similar but not identical. So yeah, it's rocket science. So it's hard, you know, it's still hard for us to put things in space and have it all work well, okay? And in the 30 minutes that you guys gave me to talk, I could have used 4 hours. I could have talked probably all 8 hours of the workday today on this stuff. I can't teach you enough in 30 minutes for you to be able to just go and dive in and work with these data, no problem. So I'm kind of dragging you into the weeds a little bit, but the main thing you should know, and I'm not the first person to say this week, and I bet I won't be the last person to say it, you got to be familiar with your data. If you're not familiar with the data that you've been assigned to use, consult with somebody who is, go to the documentation, ask questions. I've never once been asked a question about GOES data and thought, God, I wish these people would stop asking questions. Bring questions, you know. Things to look for, we talked about this earlier in the week, data quality flags. We'll talk a little bit about the data quality flags in ABI data. And I'm going to talk about some of the known issues with ABI data so you know where the pitfalls are if you're not already familiar with them. And that's going to include a pretty major issue with GOES 17 and some of the more common imagery anomalies that you're going to find. So again, part of getting to know your data, naming conventions. I'm not going to go deep into this because I don't have time, but there's a link to a PDF there that also on the workshop website, if you go to the link for my talk in the Google Drive, that PDF's sitting in there. Because I think that's important for people, whether you're using, especially if you're going to try to use any L2 products and what all the naming conventions are for those. The only thing I will focus on in this talk is this very first, the upper right part of this table, values and meanings. The very first two letters of the file should be OR. If you have something that is not OR, I don't know how you got it, but you don't want to use it because it's test data, okay? That's my job, is to test that junk. You don't want to use that for your project, you know. And if we're you to try to publish with that, I would hope the reviewers would say, nah, go back and use operational data, please. So there's an example in here. And again, there's that OR right in the front of the file. That's what you're looking for. Next thing you might want to do with data is look at the metadata. When it's netCDF data like GOES R, ABI data R, there's an opportunity at least for them to stuff a ton of really useful stuff in the metadata, right? And so here's where I'm dragging you down into the weeds. I used NC dump. That's, I think, free. I have it on Linux. And it just dumps out the header. Well, if you do a -H, it dumps out the header. If you don't do a -H, you'll feel sorry for yourself. So some of the first things you'll see in here are the dimensions of the file. I've lost my cursor. There it is. X and Y. I can't remember the file, you know, how big these things are. I forget all the time. I have terrible memory. That might be useful for you if you're coding things. The first variables in here are X and Y. Those are the projection coordinates. We don't provide you with latitudes and longitudes because that would have been super useful and easy for you. So we give you these X, Ys, and you're going to have to go to the documentation to learn how to transfer that into lat/lon. Luckily for CONUS and full disk sectors, you only have to ever do that once. It never changes for GOES East. It never changes for GOES West. For the mesoscales, if you're working with that, every time the thing moves, you're gonna, you'll have to figure this out. For the radiance, I'm looking at a level 1B radiance file here. Is what I suggest if you're trying to do math on satellite imagery, you really should be working in radiances. So that's what we're starting with. A lot of this stuff applies to the level 2 products and would in general apply to other satellite data. But what radiances are, they're scaled integers is how they store it. Now, your netCDF package, your library, is going to unscale those for you. So you're probably thinking, why do I care how these things are scaled? And the reason is radiance is supposed to be a real, like, a physical measurement, right? But if you look at this, the scale factor and the add offset, that add offset is negative. So if the first integer stored is 0, and I go through a linear equation, so I multiply the scale factor, 0 times something is 0, and then I add this negative 1 point, I get a negative radiance, which is not physically supposed to be possible, right? So you might want for your application to know what's the minimum possible positive radiance, because that's where, like, your data that's where you want to start probably, right? Like, you don't you don't want to be using negative. So you might want to know what that value is. And the reason why is from a data quality standpoint, if you do some calculations and you get something that's different from what you know is possible from the file, you know you've done something wrong. Then DQFs, again, they got pixel level DQFs. I'm going to use the Gen Z slang we used yesterday. These are fairly mid, okay? You might think they're super useful, but they're fairly mid. But they have the metadata on them is great, right? They tell you what the possible values are, 0 through 4. Don't forget they can be -1 if they're missing. They tell you what all those mean. And then they have metadata on them, and that metadata on them is what's probably the most useful. Okay, they tell you the % good, they tell you the % conditionally usable. If you're using Go 17, the most useful one's the one down there at the bottom. The % focal plane temperature threshold exceeded. If that's ever greater than 0, you should probably just not use that file at all. So I know what you're thinking. Matt, this thing's an operational satellite. Like what, NOAA puts this out, it goes out to the Weather Service. All these people are using it for decision support. What could go wrong? Yeah, unfortunately, stuff went wrong. So on Go 17, they had this loop heat pipe issue. I don't have time to give you all the details of it, but if you ever are using Go's data retrospectively and you need to use Go 17, because that's what the Goes West satellite was for a couple years, you need to know to avoid when the data are bad. So I would use that quality flag metadata that I mentioned in the last slide. But you can see there's it might be hard to read these labels. At the bottom is month. This is an entire year, the year of 2022. And these are peak, this blue line is the peak focal plane array temperature. The detectors on these satellites need to be kept incredibly cold. Okay, it's supposed to be 60 Kelvin, and if you can't read the scale on the bottom, it starts at 82 Kelvin and ends at 110 Kelvin. If I were to plot this for Go 16 and 18, it's a flat line at 60 Kelvin. So you can see this thing's just all over the place, and it heats up worse at certain times of the year, and it heats up worse at night, because at night the sun's behind the Earth, so it's shining on the face of the satellite, and the face of the satellite is where Earth-facing instruments sit. And so this loop is just going to show you what a loop with that, what happens to the IR bands. So the first 6 bands at the top of this are the visible and near infrared, and then the 7th one is band 7. It is not affected, but the other IR bands are all affected to some degree every day, and some worse than others. And you can see as you're, you can imagine what this was like for the imagery team when we got pre-first light data. And yeah, I cried a little bit. I'm not gonna lie. The calibration team did an excellent job to get anything out of it. So another imagery anomaly that you will run into if you're looking at data prior to 2019 or April 2019 is what we call cold pixels around fires, especially if you are looking at fires. If you look at this hot spot up here, this is a fire in California, and there are these little white pixels, though that's not real. It's not that cold. The remapping algorithm on ABI was a little overzealous. You had a really hot pixel in this band. It made a nearby pixel really cold. They've changed that, and so after April of 2019, all the data has that, won't have that problem in it. And then some of the more common imagery anomalies, and these are super colorfully named. And I get to, this is like the one thing I get to claim any credit for in the GOES program is I named these things, these ridiculous names. So shark fins, caterpillar tracks, and cookie monsters. And hopefully it's visually understandable why I named them that. My favorite one is Cookie Monster, because you have like dead serious engineers and calibration experts in meetings, and they're like, we have to avoid doing this during the Cookie Monster time. They use that term. No, it's really called bright object avoidance, which is a fancy way of saying you shouldn't stare at the sun. So ABI shouldn't stare at the sun either. So you'll see this, periodically. It's different times of year. It's different because, of course, of the relationship between where the sun and the satellite and the Earth are. But a key thing for you to know is that it's different for each band in terms of how much Cookie Monster bites out of the cookie. And that has to do with how the instrument is built and the way it scans. And so as soon as the first detector on the focal point array is too close to the sun, they stop scanning. And that's going to be then at different parts of the Earth for the other bands. And I'll show you what that looks like in this image. So this is super zoomed in on the right of a Cookie Monster bite, but you can see it's a totally different sized bite. The other thing you might notice is that in these visible near-infrared bands, you see some stray light. And that's super obvious in that image on the left. So even when we avoid staring straight at the sun, we still get stray light in those images. If that's going to bother you and your project, this is a time to avoid. A Cookie Monster time is a time to avoid it. Obviously, it impacts the visible near-infrared bands the most, and you're probably not using those at night. It also affects band 7, which you can see down here. This is band 7. And even band 8, which is the water vapor band. So beware of stray light. And then if you're making 3-color or you're making RGBs or 3-band composites or whatever, and you got that weirdly shaped Cookie Monster in the overlay, it just gets really, really awful. I put shark fins and caterpillar tracks together because they're very similar. They don't look similar, but what they are is when data are dropped prior to going into the remapping step, the remapper then does weird things with it. And so like with the caterpillar track, you can kind of see it's super jaggedy edged. And then with the shark fin, we're going to zoom in because it's not just the fin that you see that white. Here, this is a different case, so the fin's kind of upside down. But it's like, look at the data under that part of the fin that's like super smeared. Over here, it looks like it's actually okay, except for it's like shifted. And in this case, there was a caterpillar track in this one too. And so I know what you're thinking now. You're thinking, well, man, there's pixel level quality flags. So obviously that will tell me what data I can and can't use, right? Remember I said they were mid. So we're going to look at the quality flags. So I apologize it's in a different projection because it's easier to show quality flags in Panoply, which is a free tool I think somebody mentioned the other day. But so remember under the shark fin, data was all weird and smeared and you shouldn't use it, right? It's all flagged here. It's all blue. That's flag 0. That's a good pixel. Okay. And then in the fin itself, you've got some of these pixels are flagged red, which is good, right? That's the no pixel. That's true. The no value pixel flag. But in the middle of it, it's not flagged at all. It's got a missing flag. Okay, and then over on this far side of it, this is marked for some reason as conditionally usable. And all along the fin, you can see there's kind of these little corners that have different colors. So some of that's also marked as conditionally usable. That's not super useful, I'm afraid. And then another quirk of the DQFs is in space, we get 2 different DQF values. And the reason for this is when they build a file, they start with the fill value, which is -1. So that whole array size, whatever array size you start with, full disk or conus or a mezzo, is going to be DQF equals -1. And they only change it when they scan something and put it into that part of the array. So they don't scan the entire 5,400 pixels at the top of the full disk. They only scan this little bit at the top just to get what they need to build it. So the parts of space they actually scanned they put a no value pixel quality flag in, and the rest of it's still out there is -1. So that's just something to be aware of. So after I picked on the DQFs, how are you supposed to use them? So I be honest with you, I never use them at the pixel level unless it's to bother NOAA for not doing a very good job of making pixel level quality flags, which is part of my job, is to provide them mean feedback, which they just ignore. So that % good pixel metadata under the DQF variable, that's super useful. If you have a CONUS or a meso, that should be 1. And then it's never going to quite be 1 for the full disk because of space. And then there's a % uncorrectable L0 errors variable in the files. And I think you want that to be 0. I think if it's not 0, there's a chance you have a shark fin in your data. And then specifically for GOES 17, we talked about this already, but that % focal plane temperature threshold exceeded. Okay, if the instrument's heated up and it's too hot to give you good, well-calibrated data, we have flagged that there, and so you can avoid that data. And then there's of course brute force. You can do it yourself. If you've got a small study area, you can just look for if there are non-zero DQFs in your study area, or you can search for non-realistic radiances or whatever product that you're looking at. And the great thing about GOES is the time resolution of it. So at most, you just have to wait 10 minutes to get another image. So unless you're trying to use this in real time, if you're like, say, I'm trying to look at the brightness temperatures every afternoon over Puerto Rico. Now you get a bad piece of data for that one time. You just wait 10 minutes and you get another full disk, or wait 5 minutes and you get another CONUS. It's always better to have no data than bad data, right? So that's me bashing NOAA and GOES for a while. So I'll get in trouble if I go home and I haven't said what goes right. So we have a web page at CIMMS that we are doing a lot of the data quality monitoring from. And if you go to that web page and you click on this link here, the GOES statistics displays, we have 16 frame imagery, just shows all the bands. We do geo differences. We do these time differences that you see over on the left, which are super useful for pointing out weird things in data. And not shown on this screen capture, we also have a monitoring page now for the cloud and moisture imagery product, which is the brightness temperature files. And again, I don't have time to go into all that, but there are super weird things in that metadata with mins and maxes. And I would recommend you calculate your own mins and maxes and means as well. And don't rely on that metadata. So when we do geo comparisons, we look at this red rectangular area, which is halfway between the two satellites. We just do a mean brightness temperature in those regions and then compare them. You don't expect them to be perfect because clouds are moving in and out and there's parallax differences between the two of them. But by and large, we get really, really good comparisons. The ABI is an incredibly well calibrated instrument. And I'm not showing it in this presentation, but we did comparisons between GOES 18 and 17 when 18 was in its checkout phase, and the two satellites were almost co-located. So we had, for the first time ever, really good geo-to-geo comparisons like that, and they're really spot on. They're very consistently calibrated, so I think this is an improvement from geo for climate studies to have such a consistent record between satellites. And here's an example. This is a visible band. So I'm flipping back and forth here between GOES 17 and GOES 18. And other than the preliminary non-operational label you see flickering, you're not going to see any differences between the images. I mean, they're just spot on. And you might think this is really cool. You get 30-second imagery by using 2 different satellites, mesoscale, 1 minute, offset them 30 seconds. So why don't we do this all the time with GOES East and GOES West? And it's because of parallax. You probably don't want to stare at this too long because you get motion sickness. But so that's Salt Lake up in the upper left hand, and I just ask people, like, can you tell me when the clouds are over the lake? And you can't. So that's something else you got to know about is parallax with GOES data. And then I just have some cool animations. This is the volcanic eruption in Hawaii from this past winter from GOES 18. That's 30-second imagery. And then another one, which it's 1 minute on the left, and it's 30-second imagery on the right. And you can see people out have asked, like, why do you need 30-second imagery? I'm like, well, sometimes things change in 30 seconds. And then just a cool blowing dust. We had all 3, GOES 16, GOES 17, and GOES 18 views of this one. And this is the eclipse from 2017. And I'll just point out this is a Geo2Grid is a Python package for satellite data. It's free to use. I think relies heavily on SatPy and other tools that you guys are using out in the community. And my closing thoughts: to do ethical, effective, and reproducible science, from a data quality standpoint, I think archived satellite data should be reprocessed periodically. And I'm saying this because NOAA has no plans to do this with ABI. And you might think, well, Matt, you've been working on this since 1999. Surely you have all kinds of influence. Now, I have no influence. The people who have influence are you guys. Users have influence. So if you ever go to a GOES users conference, or you're at the AMS in a GOES session, and you get a chance to talk to the GOES-R scientists from NOAA, you tell them they need to reprocess the data and reprocess it. I think that's needed for climate studies. You can't expect people to know all the things I just pointed out, and a lot of them are fixable. For example, the DQFs right now are inconsistent because the early data didn't have that focal plane module temperature threshold. That wasn't in there in early GOES 16. That had to be added when GOES 17 had its problem. If you did post-processing, you could catch all those things like shark fins. They could either be fixed or at least be flagged at the pixel level better in post-processing. The cold pixels around fires could be fixed from the beginning of the satellite record. And I didn't go into how GOES 17 is calibrated. It's super complicated, but it would be vastly improved because now we know what the focal plane temperatures were. And so reprocessing it with that knowledge, we could have better calibration. You get more usable data out of it. And then we could add something that a lot of users have asked for, which is swath scan start times, which we've been harping on since pre-launch. But yeah, you as a user have way more power than I do as like an insider, believe it or not. So, and my last thought, of course, is get familiar with your data. Even if you don't use ABI data ever, that's, I hope, the most key takeaway you get out of this is there's all kinds of things lurking in the data. And if you don't know about them, they might get you. And I'll leave it up on some links, lots of cool, I'm sucking up to Kim a little bit. I got her webpage in there. So thank you for having me. I super appreciate being invited, and happy to answer any questions anybody has.
We do have a question online. with derived motion wind data?
Can GeoGrid work with derived motion wind data? Well, I'm sure that it can. I just don't know that anybody's done that. But it can work with any GOES-R data. It might be that you have to put some of the hooks in to read the data in, but after that, yeah.
So you mentioned there were problems with mains, maxes, and mins, and the data for, I believe, GOES 17?
Yeah, so let me be clear about that. So for the cloud and moisture imagery product, which is a CMIP file, which it's a level 2 file, and it's GOES 16, GOES 17, 18, and it'll be a problem with GOES 19 after that launches too. I don't always, when I do my own calculations, they don't always agree with those. And the mins are especially crazy. So I mentioned how to get, you can use the scale and the offset in a file to be like, hey, the minimum value that's possible in this file, because of it's a netcdf and that I'm just doing math, and I'll make up a number. Let's say you calculate it's 160, and you're gonna look at a file and look at the min in the metadata, and it's gonna be 70K. And that's not possible. So that's something I'm hoping I can get that one fixed, because I feel like that's egregious. But they haven't listened to us complain about that yet. So,
Is that due to instrument error, do you think? Or?
No, it is not at all due to instrument error. It's some weird thing they're doing when they calculate those things prior to stuffing them into the file. And I'm like, that doesn't, so because of the way the data are remapped, which we didn't really get into, there may be an on-remapped pixel that's got some weird, because it's partially in space. But I try to explain to them, like, for a user who's going to download these files, it's not super useful for them to get a value like that. So, are there any other questions?
So, going back to the less than perfect data quality flags. Visually, you look at that image and that ain't right. And even in the spots where the data flags claim that they are. Have you considered trying to train an AI model to help improve the detection of some of those errors?
Yeah, we did. We actually had a student that was working on that, and they didn't complete that. But yeah, it does. That seemed to me like the perfect thing for a AI model. But yeah, that's a great. And if they were to reprocess data, they could use an AI model to find them all.
Bunch of sample imagery to work with.
Yeah, yeah. There's plenty of good data for training sets, and we actually have a text file list of all the ones we found with those problems in it. So I saw Tanya's hand go up way a long time ago. Did you give up on your question?
No, thanks, Matt. It was just to bring attention to what was in the chat.
Oh, it was what was in the chat. Okay, thank you. My timer went off, so.